Let's do a problem now with a non-uniform charge density. Let's say we have a thin rod of length L and total charge Q. Let's just draw that rod. It has a non-uniform linear charge density, lambda of x, so lambda as it depends on x is a constant lambda naught times the position x divided by L, where x is measured from the rod's left end. That's giving us the coordinate system. So let's draw that part in. My y-axis can come up perpendicular to the rod. My origin goes at the left end of the rod. My x-axis is horizontal. So x is measured relative to the left end of the rod. Two questions to answer. What is our constant lambda naught in terms of the total charge and total length? That's part A. And what is the potential on the axis some distance to the left of the rod's left end, so over here. Let's start with part A. What is lambda naught in terms of Q and L? So why don't we get started just by making a list of some things that we know. So we know that the net charge is given by the symbol Q. We also know that we could get the total charge on this rod if we add up the charge in each little tiny slice of charge along the whole length. So that tells us that our net charge Q is the sum of all the little bits of charge over the length of the rod. Okay, let's identify a dq since we've written it down here. So dq is a charge element on our rod. So if we sum all those up, we'll get the net charge. The next thing we know is that little element of charge dq the amount of charge on that little charge element dq can be given by the density of charge, which is lambda, which depends on x, times the width of that little bit of charge. And the width of that little bit of charge is a little bit in the x direction, dx. Okay, so now what we can do is put this all together. Q is the integral of dq, where this is our expression for dq, and lambda of x is given by the function in the problem. The constant times the position x divided by the length of the rod. Okay, let's put all this together and see what we get for our answer. Q is the integral of dq, which is the integral of lambda, the density as a function of the position, times dx. And our lambda is the constant times x over L times dx. We can haul our constants out front of the integral, lambda O over L, integral x dx. We better think about the limits of our integral here. We're integrating over the entire length of the rod, so because we're adding up the bits of charge over the whole length, so we'll start on one end and we'll finish at the other end. The left end of the rod is at x equals 0, and the right end of the rod is at x equals L. Let's keep going with our integral. The integral of x dx is x squared over 2. That's going to be evaluated at L and 0. Okay, so our net charge Q is lambda naught, our constant, times L over 2. This is almost what we were asked for, but not quite. We found Q in terms of lambda naught. We were asked for lambda naught in terms of Q. So lambda naught is equal to 2 times Q over L. Where we're going to go with this next is our lambda of x is lambda naught times x over L. We're going to fill in that for our lambda naught. so we found the expression for our constant in our density function, and we're thinking ahead to the fact that now we can write our density function in terms of the parameters of the problem Q and L. Next, we'll move on to part B. What is the potential on the axis left of the rod's end? So this page is a bit full. Let's move on to a new page and a new diagram. So I'll redraw my rod. It's still got length L. I'll put that in up here. Put in my coordinate system, x and y. Still have to take x equals 0 at the left end of the rod because that's what's given to us in the problem. It says x is measured from the left end, so that's where our origin has to go. And now let's put in our point D. So the point where we're trying to find the electric potential is left of the left end of the rod. The distance between that point and the end of the rod is D. Okay, there's our setup. We know that if we want to find the potential at this point, we have to find the potential due to each little bit and add them all up. So our net potential is the sum of every little potential made by every little bit of charge, which is given by K times dq over R. Let's make sure we know what we mean by dq and R. dq is our charge element on our rod. We can identify one little bit of charge, dq. Let's label in our distance. dq is a distance x from the end of the rod. And what else? R means our distance between our point and our charge. So this is our distance R here. So R is from here to here. R is equal to D plus X. Okay, so R is from the charge to the point. D to X brings us, D brings us from the point to the origin. X brings us from the origin to the charge. So R is D plus X. Okay, what next? We can use our expression for dq that we had written down in the previous part. dq is the density times the width of our little bit of charge. That little bit of width of charge is dx. And lambda of x was a function we already have written down. 2 times q times x over L squared times dx. Okay, I think we're pretty much ready to go. We're going to put this expression in for dq, we're going to put this expression in for r, and then we're going to find our potential. So that's the integral of k times 2 times q times x over L squared, and that's all divided by r, which is d plus x, and that's integrated with respect to x. Let's haul our constants out front of that integral. So 2 is a constant, k is a constant, q is a constant, L squared is a constant. So I've got the integral of x over d plus x integrated with respect to x. Okay, now I've got to get my limits of the integral on there. I'm going to start at one end of the rod where x equals 0. I'm going to stop at the last end of the rod where x equals L. So there's my integral. I'm at 2 times k times q over L squared. You can do this integral on your own, or you could look up the result in a book. If you look up the result in a book, what you should get is x minus d times the natural log of x plus d, and that of course is evaluated at 0, L and 0. Don't want to get mixed up on my limits there. X minus d natural log of x plus d. Okay, just double checking to make sure I have it right and I didn't write something down wrong. I'm going to evaluate it at my limits, which means I'm going to put in x equals L, and then I'm going to subtract the term with x equals 0. 2kq over L squared, L minus d times the natural log of L plus d. Subtract 0 minus d times the natural log of 0 plus d. Let's simplify 2kq over L squared. L minus d times natural log of L plus d. Minus 0 minus a minus is a plus. D times natural log of d. Let's see what I can do here. I can take that d outside those two natural log terms. And then I can remember the property that if I'm subtracting two log arguments, it's the same as the natural log of those two things divided. Oops. As I came to here, let's see, I've got minus here and plus there. Yep, that's okay. No, I'm not happy with this at all. I want to take plus d outside. Yep, okay, I like that better. So I got plus d outside the natural log of d over L plus d. I suppose it doesn't actually matter with all those log identities. It all works out to be the same thing. So that's my minus, so that's in the denominator, that's in the numerator. And then, so that's our expression for the potential at the left end of the rod. And one thing we're going to know about this potential is because our rod is positively charged, this potential should be positive. Okay, and V is greater than 0 because Q is greater than 0. When I looked at this function, I couldn't tell, to be quite honest, I couldn't tell right off the bat that this was going to be a positive function, so I plotted it in a spreadsheet, and it is indeed always positive.